Previous session we have gone with the electrochemical theory of corrosion followed by the different types of corrosion. In this session let us discuss regarding the factors affecting the rate of the corrosion. There are several factors affects the rate of the corrosion process. Chief among them are given below. It is the nature of the metal and the nature of the environment. Nature of the metal. Under this factor, we have got a factor number 1. It is the nature of corrosion product. The corrosion product is usually the oxide of the metal which forms a layer on the metallic surface. The oxide layer determines the corrosion rate. If its composition is stoichiometric, highly insoluble and non-porous with low ionic and electronic conductivities, then the layer formed effectively prevents further corrosion. Aluminium, titanium, chromium develops such a layer on their surface and becomes passive to corrosion. Stainless steel builds up a thin but highly protective film which risks attacks in an extremely corrosive environment. Metals such as tantalum, zirconium and molybdenum not only form such protective layers but are capable of several repairing and oxide film when it is damaged. Hence, these are extremely passive metals. On the other hand, non-stoichiometric oxides have an appreciable conductivity and form a thick porous layer. As for example, on iron and zinc, these oxide layers cannot be controlled corrosion on the metal surface as the access to the corrosive environment cannot be completely prevented by the porous layer. Factor number 2, it is the ratio of the anodic and cathodic areas. Smaller the anodic area, the larger the cathodic area, rate of the corrosion is intense. For instance, we can take the example of tin coated on the stainless steel. Here, tin is plated on the iron such a way that some areas are not covered or some pinholes are left. These results a small anode and a larger cathodic area as shown in the figure. An intense localized corrosion at the exposed small anodic area surface. On the other hand, zinc plating on iron gives the anodic coating on iron since zinc is above iron in the EMF series. Even if zinc plating peels off at some points, intense corrosion of iron would not occur. This is because of formation of a larger anodic area and a smaller cathodic area. Factor number 3, it is the electrode potential. The electrode potential, that is the inert value, is the main factor which determines the rate of corrosion when two different metals exposed to the atmosphere in contact with each other, that is galvanic corrosion. The potential difference between the anodic and cathodic areas control the corrosion rate. Such a potential difference is referred to as an open circuit potential difference. Larger the difference in the open circuit potential, higher is the rate of the corrosion. For instance, the potential between the iron and copper is 0.78 volts, which is more than that between the iron and tin, that is 0.3 volts. Therefore, iron corrode faster when contact with the copper than with the tin. Thus, further apart the metals stand from each other in the electrochemical series, greater is the intensity of corrosive attacks on the anodic metal surface. Under the nature of environment, factor number 1, it is the pH of the medium. In general, higher the acidic nature of the environment, that is a lower pH, higher is the rate of the corrosion. At pH greater than 10, corrosion of iron practically ceases due to the formation of protective coatings of hydrous oxides of iron. Between pH 10 to 3, the presence of oxygen is essential for corrosion of iron. A case in point of this phenomenon is that ships submerged for hundreds of years remains almost unaffected. However, if the pH is lower than 3, severe corrosion occurs even in the absence of air due to the continuous evolution of hydrogen at cathodic region. The factor number 2, it is the temperature. In general, as the temperature is increased, the corrosion is accelerated. Increase in temperature results in an increase in the conductance of aqueous medium and thereby in diffusion rate. As a consequence, corrosion progress faster at higher temperature. In some cases, rising temperature decreases the passivity, which again leads to an increase in corrosion rate. Under this factor number 2, it is the polarization at anode and cathodic areas. Polarization is the departure of electrode potential from their equilibrium values, that is, from the open circuit potential causing a decrease in the current density. The variation in corrosion potential ultimately leads to the steady state called corrosion potential, at which some of the areas of oxidation, that is at anodic reaction, equal to the sum of the rates of reduction, that is at cathodic reaction. The corresponding to this corrosion potential is called corrosion current. This depends upon the several factors. If the anode alone undergoes polarization, the rate of corrosion is controlled by the anodic polarization. The anode polarization, a galvanic series. As we know that the galvanic series, that is the activity of the metals in the corrosive environment, determines the rate of corrosion. In general, a galvanic series is an EMF series. Base metals are placed higher and the noble metals are placed lower in the series. It may be seen from the above table that aluminium and nickel are more noble than that indicated by the EMF series, and titanium behaves like a true noble metal. Thus, the galvanic series is more useful in studying corrosion. Some important characteristics of the two series are summarized below. In the electrochemical series, E0 values are measured in pure metals dipped in their solution without any oxide films on them. Galvanic series, on the other hand, is developed by studying corrosion of the metals in the environment without the removal of their oxide films. The position of galvanic metal is fixed in the electrochemical series, whereas it may vary in the galvanic series. It depends upon the corrosive environment. Corrosion characteristics of alloys can be studied using this galvanic series.